Hey everyone, we're so excited to see you here today to come and learn a little bit about the hoist rooms and the Yates shaft and some of the cool stuff that's here. My name is Nicol Reiner and I work with the education and outreach team at Sanford Underground Research Facility. And I am joined here by Chantel as well, and I'll let her introduce herself in a moment. I just want to tell you a little bit about myself. I actually was a secondary mathematics teacher in South Dakota for many years before I went to the Department of Education and then came to Sanford Lab. And I'm so excited to be here, although I just started in March. So this is a new place for me too. And it's so exciting to be here. So I'm gonna let Chantel introduce herself and then we'll get started today.
Hi everyone, my name is Nicol Reiner. I'm a senior with Black Hills State University and I'm an intern this summer working with the SURF Education and Outreach Program. And I'm lucky enough to be a part of Neutrino Day and help out Nicole today.
For sure. Thanks, Chantel. So this session is going to be filled with things to notice and wonder. We really want to think about the different parts of the lab, particularly the hoist room, and we want to think about what do we notice when we see images or videos or think about it, and what do we wonder? So we're going to encourage anyone who's watching to put their notices and wonders at any point during the session in the comment or the chat box. And there will be a couple of places where we actually say, hey, we're looking for your notices and wonders right now, but you can put them in at any time and we will be watching those so that we can talk about them and think about them with you. If you noticed on the website, actually where our session is, there is a PDF there. You don't necessarily need it in the beginning. You can wait until the end. But we're going to pose 3 big challenges throughout our session. And those challenges are on that link on the site. So if you would like to take a peek at it, you can, or you can wait until the end as well. So I'm so new at the lab that I haven't been underground yet. So I'm very excited to be able to get underground. And so Chantel, have you been underground?
I have actually in February for one of my science classes. It was microbiology with Dr. Bergman at Black Hills State. I was able to go underground to help with collecting biofilm samples for some research he was doing. So that was a super great experience, and I'm really glad that I took advantage of that opportunity.
That's cool. So I'm actually going to share a picture of one of the ways the underground looks. So here's an example that you guys can see on the screen. It's not Chantel. I wish I had a picture. Actually, probably could have found a picture of you, Chantel, underground. But here's a picture of some folks who are doing some work underground in the caverns that are not completely finished like a lab. Was this similar to what it looked like, Chantel, when you were down there?
Yep, spitting image. I recognize the tunnel or the tracks you can see there on the floor and the little puddles that are accumulated everywhere. And then, of course, you see the metal sheeting up top with those bolts sticking out, and that was everywhere in the tunnels. It just holds that structure in place, and we were able to scrape the biofilm from the rocks on the walls and get it out of the water that was sitting there too. It was awesome.
That's cool. Very cool. So throughout this session, Chantel and I are going to talk about several different things, and like I said in the beginning, we want you to notice and wonder things right along with us. But also then we're going to post some challenges, and then 1 week from today, I'm actually going to post the response to the challenges. So you won't get to find the answers out today. You have to do some thinking and some problem solving to figure them out. And then also on Tuesday of next week, and I'll let you know this at the end too, but Tuesday of next week, I'll post some hints for some of you that might just need a little nudge to go in the right direction. All right, so let's take a look. I want to actually show a couple more pictures. We're going to go underground again, but we're going to look at what the cavern would have looked like in the time of Dr. Ray Davis. So this picture is actually one of the pictures when Dr. Ray Davis was completing his explorations down in what's now called actually the Davis Cavern. And that's one picture I want you to think about, notice and wonder things. And then this is another picture that shows a little bit more completion when he was down there doing his experiments, and he was looking for neutrinos, and he actually won the Nobel Prize in physics. So it's these pictures themselves actually create some interesting things to think about, when particularly their size. So important to think about that. So with that being said, one other thing, actually, one of the original rings from this isn't down there anymore, but one of the original rings from this particular science experiment, from this particular setup, is actually at the Homestake Mine Visitor Center in Leeds. So you can go and you can see how big it was, and you can imagine it being underground, which is kind of fun.
So I have a quick question.
Yeah, what's your question?
It is about Dr. Ray Davis's experiment. So when did he start building the first physics experiment underground at that 4850 level?
So this is a great time for a trivia question. So everyone take a peek at this question. And while I'm going to talk a little bit while you think about your answers, for those of you who are watching, because he won the physics, or the Nobel Prize in Physics, in 2002, or he was awarded actually the Nobel Prize. And because his experiment was the very first one to actually detect neutrinos that were emitted from the sun. So his experiment actually caused a little bit of a stir in the scientific community, because he expected to find a certain number of neutrinos with his detector, but he actually only found a third of the neutrinos that he expected to find. And so there were some folks who thought, maybe his experiment is flawed. But he persisted, and he kept thinking about it and talking about it. And what he figured out is there's actually 3 different kinds of neutrinos, and they're called flavors, which I find interesting. So 3 different flavors of neutrinos, and his detector actually only detected one of those flavors of neutrinos, and they figured that out, which is very cool. So Chantel, I see this up here. Do tell, what is the correct answer? When was he actually starting to build his first physics experiment?
It was in the 1960s.
1960s. This is actually surprising to me, that it was so long ago. I figured that it would be much later. I didn't realize there was such an overlap actually between the science that's happening now in the Sanford lab, the science that happened then, which builds on it, right? Or that was the foundational block, and the actual mining days. So that's super interesting. All right, so let's take a look at actually a couple other pictures from underground. So here's one here, and this is the picture of the LZ dark matter experiment. So this is down at the 4850 level, 4,850 feet below the surface. And this experiment is looking for dark matter. And it actually, the experiment is actually includes 220 participating scientists from 38 institutions around the world. So it's really cool to think about how many different people are impacting and figuring out the science that's being studied with this particular experiment. One more experiment, or one more picture that I actually want to show you, is this one. This is part of the Majorana demonstrator experiment, and it is actually trying to answer one of the most challenging and important questions in physics right now, and that is, are neutrinos their own antiparticle? Which blows my mind, actually, to even think about this. But it is kind of an interesting, picture of what it looks like underground, and it's big. It's very, very big.
So I do really enjoy seeing the pictures of everything that's going on in the lab underground. It's incredible to see this stuff. But you had mentioned at the beginning that we're going to be talking about the hoist room, right?
Oh yeah, we should probably think about that. So just the thing though, that hoist room is pretty darn important, because none of these experiments that have been built 4,850 feet below the surface would be possible without the Nordberg double drum hoist that lives in the hoist room. And the Yates shaft that actually connects the hoist room down into the underground levels. So these experiments would not be possible without such an apparatus, I guess is the word I'm looking for.
So this cage must be This hoist must be huge. It just must be a massive piece of equipment to be able to get so many people underground and all of this other equipment that's needed for these experiments.
You know, so that's an interesting point because the cages themselves are not very big. Let's see if I can. Here's a picture of the one of the first cages that was used, and that cage is like an elevator. So it's the form of elevator that's connected to the hoist that gets things down below the surface. So this particular cage actually sits right now in the Homestake Visitor Center. So you can stop by and visit it and step inside and see what it would be like to actually be in the cage and go down to the 4850 level or any other level that a scientist might be visiting. They've actually just installed a newer cage recently. And we'll take a look at that one as well. So here's a picture of them putting in this new cage. This one is a little bit bigger. It's actually 9 foot tall. It weighs 14,000 pounds. 14,000 pounds, that's a lot of weight. And it was made specifically to make sure that some of the largest parts of the experiment could make it down into the shaft. In normal cases, in normal operation, you can actually have about 28 people in this particular cage. So that's something to think about when you look at those guys that are pushing the cage in there. There's not a lot of space for 28 people that might be in the cage. How many people were in the cage when you went down?
I think it was a pretty full ride because you're packed in there pretty tightly. So there's just a couple of inches of space between you and the other person. And since they have scheduled cage rides at certain intervals of time, they try to fit and make it a full occupant ride.
Yeah. Well, and I giggle sometimes because when I go to my office at the Sanford lab facility, I'm on above ground in where I do my work with education and outreach. But the same door that I go into is the one that some of the scientists use to get down to the cage, actually. And I see them running at times in the morning because the cage, as I've heard said before, the cage waits for no one. So if you miss your cage, you're done. They don't come back up and get you. So it is interesting in the morning to see some of those folks in a big hurry to make sure they make it to their cage. Okay, so what's interesting to me about this, and I'm going to show one more picture here before we talk about a couple other things. And this is a picture of a ship in a bottle. And when we think about, somebody else used this analogy, and I really love this analogy. When we think about the huge things that we saw that were underground, all of that has to fit into the cage that goes down. All of it has to fit piece by piece. And then it actually has to be constructed and created and it's designed beforehand, but to get down there and then built to the design that was made. But it's also the cage and the hoist are also the only mechanism for getting people down there. So that's really cool too, to think about that. That is a very important part. And the hoist has to work in order for all of that to happen. All right, so let's see here. I kind of wonder, since I haven't been down in the cage, I kind of wonder what it would be like in the cage to go down to the underground lab. So we're going to take a look at a little bit of video here. I'm going to stop sharing my screen so that we can make it possible for video. So we're going to take a look at a little bit of video, and there actually are going to be two chunks. One chunk is going to be a cage ride from inside of the cage. And the second chunk is going to be a piece of the cage ride, and they're both pretty darn short, but a cage ride from the outside of the cage. So I want you to watch both of these little snips of video. And while you are, I want you to keep putting notices and wonders in the chat box. So things that you notice and wonder about these cage rides. And I did actually see there was a wonder from earlier that I missed. In the photo, is there rust on the floor? I don't know the answer to that. I'll have to do some investigating to figure that out. So I want you to watch these two little pieces of video. I want you to notice and wonder. And as you're watching them, go ahead and type them into the chat, and then we'll talk about them after we're done watching the video. So go ahead with the videos. All right, so you got a chance to look at a couple of snippets of video. So now I really want you to think, and I want you to wonder, what are your questions? What would you like to know more about? And while we're allowing time for people to type some things into the chat and into the comments, I know that Chantel, you got a chance actually to ride in the cage. I have not had my chance yet. So can you describe a little bit about your experience in the cage?
Yeah, what the video show is pretty much exactly what it's like. You're all packed in there. There's no light, so it's dark, and you can turn your safety hat light on. As you're going down, you can see the wood that the shaft and lift area is made out of. It's pretty cool. And then one thing that does happen is some parts there's some dripping water that gets in there. So sometimes you'll end up standing in a position where you might be getting hit by a little bit of water, but it is so fun. It's so cool. And it didn't seem like it took a very long time, and it went at a pretty good pace. I think it took about 12 minutes to get down there.
Cool. Did you get wet when you were in the cage?
Yeah, just a little bit. It just dripped on my shoulder a little bit. It wasn't anything too crazy.
Was it, my wonder is, was it scary? Was it a little bit scary to have because it's dark and so it's just the headlamps, right? So was that, I don't know, was it creepy?
I don't know. I just thought it was really cool, because they use these things every day and make several trips every day, and you hear about the history and how long it's been around, and I felt pretty safe in that lift. I wasn't too concerned with anything terrible happening.
That's good. That's good. So we're starting to get some notices and wonders in. One of the ones that I see here is when the cage travels in the shaft, there is a gate. Oh, but in the visitor center, it doesn't have a gate. That's true. So the gate itself isn't part of the cage. It's part of the shaft that the cage rides in. So you're right. There, for those of you who are noticing that, it doesn't have an actual gate on it, which is interesting because an elevator does, but this one doesn't. Also, I'm seeing someone notice that when the cage is traveling in the shaft, it looks like it's in an unfinished apartment building. I think that looks like that too. That's interesting. One more wonder that's come in: how fast is the cage going? And so that's an interesting question, because we were just talking about that it doesn't seem like it takes very long to get down there. It takes about 12 minutes actually to get from the top of the shaft all the way to the bottom. What kinds of things did you wonder, Chantel, when you were looking at the videos? Was there anything that you wondered about?
I did wonder about the wood in the shaft. One thing I am curious about is how often they have to replace that wood. I know they do a lot of maintenance every week on the cage just to make sure things are running smoothly. But yeah, it was really interesting to see the wood through the gate on the cage. And it just really makes you wonder what that structure looks like and how they put that together.
Absolutely. I also wondered how many people could fit. And actually, I know now because I did a little bit of research, but when I first saw it, I really wondered how many people could fit in the cage. And then I wondered if it was hard to breathe, because it seems like it might be, but you didn't say that it was. So that must have been something that you didn't notice, or that wasn't the true, wasn't something that was true. I kind of wondered what it sounds like. Like, does it sound like it seems like it might sound like a train going down the tracks.
Yeah, I think that's something that you could compare it to. It's, heavy machinery going down a shaft, that kind of sound, not overly loud or anything, but it does make noise.
Sure. Some other wonders: what is the biggest piece of equipment that could fit? What is the cage made out of? Oh, and how often do they have to bring things down as slung loads under the cage? Because actually there are times that they have pieces of equipment that can't quite fit in the cage, but they can lift the cage up and attach it to the bottom, and it hangs there. Then they have to go really slow to make sure that whatever's hanging doesn't hit the side of the cage, and then it goes down. I don't actually know how often they bring things down as slung loads under the cage. I might have to do a little more research to figure that out, because someone's wondering that. So there were lots of notices and wonders, and this is awesome, because there's lots of ways we could go to explore. As a former teacher, these things are exciting to me because then I think, okay, how do we get excited about them and then go find out information to answer our questions? So I think we've come time for our first challenge, actually. And the first challenge that I think we want to think about is what is the speed of the cage? So someone asked that, how fast does it go? I think that's the one that I think we're going to make the first challenge of the ones that we talk about today. What is the speed of the cage? I actually want people to figure it out in miles per hour. And part of why I want you to figure that out in miles per hour is because then when you think about riding in a car, you can kind of have a comparison for what it would feel like with when you find out the miles per hour of the cage. So first challenge, what is the speed of the cage that goes up and down today in miles per hour? What do we know already that would help us to solve this problem?
Okay, so you did mention that it's going from above ground down to the 4850 level, so there's your distance. And then we did mention also that it took about 12 minutes for the cage to get down.
Great. Okay, so for those of you who are following along and are going to figure out this challenge to be able to submit what you think the answer is and how you know that's true, those are some things you're going to want to note because they'll be important for your challenge. I actually think we should add another part to this challenge, though, because I found out that actually when it was in mining days, the cage went at a much faster pace. As a matter of fact, it was a little scary to me how fast it was going. You said, Chantel, that your trip took 12 minutes, right?
Right.
Right. So their trip actually from the surface down to 4850 took only 3 minutes. 3 minutes.
Where that's 4 times as fast.
Yes. So I'm kind of thinking that roller coaster ride, right? So there's some parts that are slow and there's some parts that'll be faster. That might be a little too fast for me, but that's the second part of the challenge. So the second part of the challenge is for any of you who are watching, how fast in miles per hour did the miners go when they were making it down to the 4850 level in only 3 minutes? How many miles per hour? So that's not the second challenge. That's the second part of the first challenge. And so if you look at the document at the end that has the challenges on it, important information that we just mentioned to help solve that part B of the first challenge. Okay. Let's see.
So I have another question that doesn't necessarily relate to the math of the hoist and the shaft. But when was work on the Yates shaft started? When did that begin?
Oh, so that's a good question. So let me share that question so people can see it on the screen. So the cage itself goes down into the Yates shaft, and the process actually. So I was learning about this as I was preparing for this session. Did you know that they don't actually, in my head, they create a shaft from the top down, which now that I think about it seems odd, but it seems like you would just start digging a hole and then you bring up the stuff, but that is not actually how the Yates shaft was created. So when they began work on the Yates shaft, they already actually had some, I call them tunnels. They're actually called drifts. They had some drifts that were already in place. And in those drifts, they burrowed over and they actually started at the bottom of the Yates shaft and then they worked their way up, which was really interesting to me. I didn't realize that that's how shafts were built. So somebody has submitted a question, so I want to answer this question too. 4850 level means 4,850 feet distance, and that is correct. 4,850 feet in the distance. So Chantel, help us out. When was the work on the shaft actually begun?
In 1939.
1939. And that's even earlier than I thought too. Because you think about that, how long does a shaft actually get to be used? And I think it's actually usually around 50 years, but I know they do maintenance to keep it going for longer. So the shaft actually goes down for about 5,000 feet. Oh, and I think do we have one more? I think we have one more trivia question.
Yes. Yep. So based on when they started working on the Yates shaft, how many years did it take for them to get all the way down to the 48th floor, I guess?
Yeah, so all the way down to the 4,850 foot level, how many years did it take? Okay, so we'll let our viewers think about that for a moment. And while they do, so we actually have, it's already all the way down to the 5,000 foot level at this point. And they have drifts or tunnels, drifts as low as 8,000 feet. Although this shaft doesn't go that low, and they're filled with water at this point. So they're not used anymore down in that 8,000 or even just below the 5,000 level. So hopefully that little bit of information gives our viewers enough chance to commit to an answer. Chantel, what's our number of years?
It took them 15 years to complete it.
Yeah, 15 years. That's a long time. And I wonder, it makes me wonder if they could have used parts of it before it was completely finished. I'm guessing not. And I know there were other shafts as well. As a matter of fact, the Ross shaft was completed before the Yates shaft was. So they were already using that one. So that gave them, and there was another shaft called the Ellison shaft as well. Okay, so there's another piece of information that, or a story actually, that's going to put us into what we need for the second math challenge for today. So there's a story that says that one of the engineers who worked on the shaft used to drop his measuring tape occasionally down the shaft. And my assumption is it was an accident, but as I have heard some people tell the story, it sounds like maybe they did it for fun as well. I think that might be kind of fun. So the story goes that one time when he dropped it down, they actually timed the drop from the time he let it go from his hand, just a straight drop, until the time that they heard the hit at the bottom of the shaft. So they heard the tape measure hitting a surface. And the time that they measured was actually 18 seconds. So 18 seconds. So that is the second math challenge, actually. And there's three parts to it, three parts to the second math challenge. One is if we figure acceleration due to gravity, like we know that it's going to go faster, right, as it continues to go down because of gravity. How long would it actually take for the tape measure to fall all the way down to 5,000 feet? Because the bottom of the shaft is at 5,000 feet. So how long would it actually take for it to get all the way to 5,000 feet? And then the second part of the challenge is once it hits, the sound actually has to travel back up and get to the ear of the engineer. Oh, it rhymes, ear of the engineer. So both of those times would have to be included in the 18 seconds. So how long does it take? First part of the challenge, how long would it actually take if the tape measure fell all the way to the bottom of 5,000 feet? Second part of the challenge, how long would it take for the sound to go from where it hit back up to the engineer's ear? And there's one more part of the challenge. And the third part of the challenge is, did it actually hit the bottom? So we know it took 18 seconds, and you'll have to do some, for those of you who are watching, you'll have to do some figuring about how long it takes to get to the bottom when we figure in gravity, how long the sound takes to get to the top. So you'll have to do a little bit of research to find out what the speed of sound is. And then you can figure out whether or not it hit the bottom. And if it hit the bottom, how do you know for sure? And if it didn't hit the bottom, where did it actually hit? So this is a tough challenge. The third one is a tough one. So it'll be interesting to see if we get some responses later this week. Okay, so we've talked about some of the experiments and how important the hoist room is to getting them down into the underground. And we talked about the cages, and you talked about how interesting and fun it was to actually go down in the cages, which is cool. But we haven't actually seen a picture of the hoist yet. So I'm going to pull up a picture of the hoist so people can see what that actually looks like. So the hoist, this is a picture of the hoist right here in the hoist room. So I'm just going to pause for a minute, and all of you who are online, I want you to think about some notices and wonders when you look at this set of drums for the hoist in the Yates room. So take a moment and just kind of observe. Type in any notices and wonders you have. And as a selling point for any of you who are watching that haven't yet seen the virtual hoist room tour, which is linked on the Neutrino Day page, I really encourage you to watch it. It's fantastic. And you get to see it from several different vantage points. You get to see what the outside looks like. So I really encourage you to watch that virtual hoist room tour because it is awesome. Okay, it looks like we have a few notices and wonders that are coming in, which is great. See if I can, there we go. Ooh. Okay, so before we give all the notices and wonders though, I actually want you to watch a little piece of video. So we have a little chunk of video, and I want you to take a moment and watch the video and continue to think about what you notice and what you wonder. So if you guys can play, help us out by playing that video, that'd be great. And everybody take a peek at it and notice and wonder, put it in the chat. All right, so you got a chance to take a peek at that video so you can add maybe some additional notices and wonders. There are some notices that are coming in, so we can start to talk about a few of them that are coming in. One of them was, did the hoist get, a wonder, did the hoist get installed the same year that the Yates shaft was begun? And I don't know if it was the same year. I actually think the hoists might have started being installed slightly before. And I only say that because in the history that I read, it talked about the fact that the hoists were installed in the late 30s. And we know from what Chantel told us earlier that the hoist or that the Yates shaft was started in 1939. So it was about the same time. But I kind of think that maybe the hoist came first, and they didn't come together. They had to be put together. So it was a big project to put them together. Ooh, I see another wonder. I wonder how it is powered, which we're not going to talk a lot about that in this session, but there's some cool science about the current that's used to power the hoist, because it comes in like, I'm going to say this backwards probably, but it comes in either AC and it needs to be transferred or translated into DC, or the other way around.
Yep.
Interesting. Is that right? Oh, thanks, Chantel. Ooh, why are the two small wheels not turning? Oh, like the dials that are there. Ooh, we're going to talk about the dials in a moment. What wonders do you have, Chantel, or that you noticed or see?
Well, you had mentioned that there is a rope that goes around the hoist. Have you said how much rope fits on there?
Oh, that's a good question. No. So actually, the whole rope itself is 6,000 feet long from the beginning all the way to the end. But there's actually only grooves in the hoist for 5,600 feet of the rope to fit on the drum itself. So when you watch the video and when you see the pictures, you can see that, I mean, there's more rope than fits on the drum, but 5,600 feet of rope that actually fits in the grooves on the drum. And if you watch the hoist tour, you'll know this already, but the ropes never cross over itself because it prevents the wear and tear, or at least lessens the wear and tear on the rope itself. Any other notices and wonders that you have?
I think that's all I noticed.
That's all you noticed? I actually see a couple more that are coming in. What are the colorful parts of the hoist? Oh, so there's so many parts. I don't exactly know from that question exactly which part of it is, but that's an interesting wonder, like what parts are the different colorful parts? And how does the hoist operator know he or she is in exactly the right spot? That's a great wonder. And the thing to think about with that is that the hoist operator actually communicates by two-way radio with the cage operator. So there's someone in the cage and they communicate back and forth. And so they use the dials, and we'll look at the dials in just a little bit. But also they communicate with each other to let each other know how to stay safe and where they are in the trip, which is very, very interesting to me. Do you remember, Chantel, hearing the cage operator talk during your ride? Do you remember anything about how that was, or what he or she said?
No, I don't remember exactly what they said. I just know that there was somebody in the cage that had their radio and giving them the okay that they could, start moving the cage.
That's cool. One of the other wonders I had is I wanted to know how big the hoists were. So when I first started working at Sanford Lab and the education and outreach team, I did get to take a tour of the hoist room and just kind of learn about all the features and how it worked. And I just kept staring at how big they were. And actually, I think I might have one more picture to share that is an interesting, it talks about the bigness of the hoist, or it shows rather the bigness of the hoist. So you can see, so on here, you can see some colorful parts. I can see the bolts here, and there's a plate here that's green. But what I want to show you actually is this is a picture of Becky Bundy, who is one of my colleagues on the education and outreach team. And she's amazing. She has a doctorate in, I'm going to say it wrong now, but I think it's microbiology. But look at the wrenches next to her that are used to work on the hoist. Like, they're absolutely ginormous, like some as big as her head, and the bolts that are sitting up top in the windowsill. So that made me truly wonder, like, how big is this thing? And of course, being a previous math teacher, that makes me excited about the things to think about there. And the other thing that I noticed, and I'm actually going to go back and note it on the picture, is that they have an odd shape to them. So they're kind of like a cone shape. They're not an even cylinder where they're the same diameter all the way across. They're actually more like a cone. So that made me wonder about just the size of them from that perspective, and why. It made me wonder why they were shaped that way. Do you ever, Chantel, do you ever ride your bicycle? Or do you ride bicycle?
I do, yes. I
do too. And I never really thought about how the gears worked until actually I started to look at these particular here, and then read some information about why they were shaped that way. So do you have a bicycle? Do you go mountain bike riding?
Yeah, I have just a 5-speed, or I don't remember how many speed bike it is, but yeah, changing the gears, and you notice that there are bigger gears on one side and smaller gears on the other, and it interchanges.
Yeah, and I'm a lot older than you, and I've ridden mountain bikes for a long time, but I never really thought about why or how they worked. And then I started to look at this, and there's some science behind it for sure, but that the smaller gears are the gears that are smaller in diameter are actually the ones you want to use, or that you do use, when you're going up a hill, because it gives you more torque. And that is why these particular drums have their interesting shape, is because the person who designed them figured out that it would be important, because the load is so heavy and the rope is so heavy, that they needed to have some additional way to get torque, or to have more oomph to get them up, the loads up to the top of the shaft. And so they actually built them this way, so that, like a bicycle, when the load is really far down and needs a lot of effort or energy to get started, it's actually on the smaller end of the drum. And when it needs less energy, because it's towards the top, and it's already got some momentum going, it's on the larger end of the drum. So that was really interesting to me. Okay, so let's see here. So one more picture, I think, actually, before. Oh, no, we're going to go to a trivia question first. So when you work at the Sanford Lab as a hoist operator, you actually have to go through some significant training. You can't just decide to be a hoist operator and then start the next day. So I would like those of you who are watching to think about and guess approximately how much on-site training do you think is required to become a hoist operator for Sanford Lab? So you've got 4 options there: 2 months, 6 months, 1.5 years, or 3 years. So how much on-site training? And while you're thinking about that, I'm actually going to go to one more slide and show you a picture of the dials. So somebody asked before, like, how do they know where the lift is? And the lift itself, they can tell by watching the dials, and you can see the numbers, and those are the levels, so to speak. So up on the right-hand side, you can see the number 48. So like the 4,800 level. And then actually in red, so I'm looking at my screen now too, in red, you can see, I think it's 48 and a half. So 4850 level. So they use those dials. And then actually, you can't see it on this picture, but the drums themselves also have some calibration. So when they get close, they can look at the drums. All right, so let me go back to the question. Approximately how much on-site training? I know you know the answer, Chantel, because we talked about this before, but did it surprise you before you knew?
Yeah, it really did. I was very, very shocked to know that it takes 1.5 years until you can operate that hoist on your own. Mm-hmm. So it must be a pretty big job. You know, the safety of the people in the cage is important. And of course, bringing the equipment down because it costs a lot and you don't want to break it. So it makes sense, but still very shocking. 1.5 years. Wow.
Mm-hmm. Well, and these particular hoists, the Nordberg double drum hoists, the particular ones that are at Sanford Lab exist nowhere else in the world. Like, these are the only ones that exist in the whole world. And I think there were 7 of them made originally, 4 of which are still in use, and 2 of the ones that are in use are the ones at the Yates lab. So the other thing is it's so specialized because there's nowhere else to learn about how to work or fix or maintain any of these hoists, which is super interesting to me, very unique. Okay, let's see here. Let's talk a little bit about the last challenge, which is all about, for me, the shape. So when I went to think about the 3rd challenge, the very last thing that I wanted to propose as a challenge for people to work on and figure out, I thought about when my first trip into the lab, into the hoist room rather, and the things that I was amazed by. And so I walked around and I looked at the hoists, and I really wanted to know how big they were. And I was really fascinated by their shape too. That seemed odd to me that they had that shape. So I started to do a little bit of research, and I found out some information. So I found out that the smallest end of the drum has a diameter of 12 feet. So I was excited about that. I'm like, okay, cool. So I can work with that information. The largest end of the drum actually has a diameter of 25 feet. So then I wanted to know, how far was it from the beginning to the end? And that's where I can't find any information. So I couldn't find it listed anywhere. Now I could technically try and go measure it, but they're too big really to just take a measuring tape and measure them. And I don't think the hoist operators would be very happy with me if I walked in and said, I'd like to measure the hoist. So I had to look for a different way to figure it out. And the different way to figure it out is that we know that the rope that can wrap around in one layer around the drum it has grooves for 5,600 feet, 5,600 feet. And I needed one more piece of information, and that is that the rope itself has a diameter of 2 inches. So I just gave a bunch of information. So the diameter of the narrow end of the drum is 12 feet. The diameter of the wide end of the drum is 25 feet. The length of the rope that fits on the drum is 5,600 feet. And the diameter of the rope is about 2 inches. So once I knew all that information, I played with it. And of course, I taught math, so I liked playing with it. I made my kids do some calculations with me. We spent an entire afternoon actually thinking about this. And And we drew some pictures and we did some calculating. And indeed, you can figure out actually how long it is from one end of the drum to the other. And that is the last challenge. The third challenge of the day is for you all to take the information that I had and see if you can play with it and figure out how far it is from one end of the drum to the other end of the drum. So actually, let me show you one more picture because I want to make sure that people have an understanding of what I'm talking about. So here it is. Now I took a picture offline to, or a diagram, and I had to turn it sideways. The letters are sideways, so I apologize for that. But you can see that one single drum on the side there, and the narrow end, the end that's closest to those green bolts, if you measure around there, that, or excuse me, if you measure across there, the diameter is 12 feet. So you'll also, I don't want to give you too much information. I'm going to give hints on Tuesday if you get stuck, but we're going to start with that, 12 feet. The bigger end, which you can't really see, it's on the back side of that picture, is 25 feet. That's the diameter. But what I want you to find is that length L on that diagram there, the length L along. So if we measured along the rope, how long would it be? If you're really ambitious, you can try and find H as well. You certainly can find the height. If you measured through the center of the drum, that you can do that as well. But that is the challenge. How far is it from one end to the other if we measured along on the side of the rope? So as a reminder, you can find the link on the Neutrino Day website for this session for the worksheet that has the pictures and the questions. You have to get the information from the session so that you can plug that information in to solve the challenge. And you can submit ideas and work and additional questions to explore through the comments on the Facebook page of this particular session. So I'll be watching those comments to see. I'd love to see if some of you figure it out. And I don't just want to see your answer. I'm a math teacher at heart and always will be. I want to know how you got there. So I want to know how you know that your answer is what it is. So make sure that you show me your work. You could put a little snippet of video if you wanted to tell me how you figured it out. That would be awesome too. But I will be watching the comments on that session. And if you have additional questions or things that you think would be interesting to ponder, you can submit those because we will be continuing to look at the math of Sanford Lab and the math of things like the hoist room. So your questions could be great food for another conversation. If you come back to the comments section on the Facebook page, I'll put a hint there on Tuesday, a hint or two in case you get stuck. But I will tell you that you don't need anything more than the math that you learn through, you might be able to get it through geometry in 8th grade and Algebra 1 as a 9th grader, but there might be a little bit of high school geometry in there too. But any of you who are in high school and some of you who are in middle school but have a solid understanding of geometry, you can do this. You can figure this out. So I'll put the hints up Tuesday, and then on Friday of next week, I'll actually post some responses and hate to say answers, but yes, answers and how you got there on Friday of next week. So thanks, Chantel, for helping me out with this session. I wrangled Chantel. Actually, she volunteered very kindly to be with me for this session so that I didn't have to be by myself. Plus, she's actually been underground and I haven't, so I needed her expertise in that area for sure. Thanks for joining me. And thanks to all of you who are watching online. I cannot wait to see some responses for figuring out each of the 3 challenges and more importantly, how you figured it out. So I will look for that. So we wish you all a happy Friday, and we look forward to seeing your responses on the Facebook page. Thanks so much.